Welcome to today's Explainer, where we're going to pull back the curtain on the hidden mechanics of our universe. Right now, literally all around you, there are invisible forces constantly colliding, radiating, and pulling on the physical world. It's the hidden engine animating everything from the smallest specks of dust to the technology you're using right this second. Now, it can seem like pure magic, but it's actually the absolutely fascinating physics of electric fields. I am so thrilled to guide you through this, because once you understand the hidden architecture of these fields and their effects, I promise you'll never look at the physical world the same way again.
To demystify all of this, here is our quick roadmap for today. First, we'll explore the magic of charge. Second, we'll shrink down to look inside the atom. Third, we'll unpack Coulomb's law of force. And finally, we'll actually map out the electric field itself.
Okay, let's dive right into this by starting with our first section, the magic of charge. And to do that, we need to begin by looking at a real-world physical mystery.
Think back to a classic childhood trick, right? If you rub a balloon against a sweater, that balloon becomes charged. And because of this new charge, you can press it against a wall and it just miraculously sticks there. But here's the real mystery. If you take that same rubbed balloon and place it right beside another balloon that's also been rubbed against a sweater, they don't just sit there. Instead, there's a sudden, invisible snap. The balloons will actively and seemingly magically fly in opposite directions. So what is animating this sudden kinetic reaction?
Well, the invisible force driving this dynamic motion is known as electric charge. It's actually a fundamental property of matter itself. Think of this property like an invisible spring, aggressively pulling objects together or violently pushing them apart. And it all depends on one absolutely crucial factor: whether those charges are positive or negative.
And this brilliantly illustrates the ultimate rulebook for how matter interacts. It's a strict duality. If objects are oppositely charged, meaning one is positive and one is negative, they'll attract each other. But if they share the exact same charge, meaning they're both positive or both negative, they forcefully repel. This is exactly why our two balloons, which gain the exact same type of charge from the sweater, violently push apart.
Now, scientists measure this kinetic effect using a unit called the Coulomb. Imagine it as a specific, standardized package of electricity moving past a single point in just 1 second. It basically gives us a standard way to quantify this otherwise totally invisible force. But where exactly is this charge coming from in the first place? To answer that, let's move to our second section, shrink ourselves all the way down to the microscopic level and investigate the chemical suspects inside the atom.
Atoms are the basic building blocks of literally all matter, and they're made up of 3 types of subatomic particles. Let's look at exactly which ones carry this pushing and pulling power. Protons carry a positive electrical charge. Electrons carry a negative electrical charge. Neutrons, well, they're completely neutral, meaning they carry absolutely zero electrical charge. So it's the protons and electrons that are the true actors creating these electric forces.
Now, most objects in our everyday world are actually electrically neutral. They have a total net charge of 0, which just means they have a perfect balance of protons and electrons canceling each other out. For our balloon to exert that magical sticking power we talked about, it had to actually steal some electrons from your sweater, creating an imbalance. An object has to have an excess of either electrons or protons to be considered charged.
So just how much charge does one of these tiny particles hold? Well, one way to quantify it is by using a specific constant, 1.602 times 10 to the negative 19th coulombs. That is an incredibly long string of decimal places, right? But it represents the absolute minimum baseline of charge possible. An electron has a negative charge of this amount, and a single proton has a positive charge of this exact amount. So if an object has an excess of, say, 10 electrons, it carries a charge of negative 10 times this impossibly tiny constant.
Knowing what these tiny particles actually are, we're ready for Section 3, Coulomb's law of force. This is where we transition from knowing what this force is to calculating exactly how much force is generated by these interacting charges.
To measure the force between charges, we have to introduce a pretty clever concept called the point charge. Technically, a true point charge doesn't exist in reality, but electrons, protons, and other particles are so incredibly small that physicists use point charges to approximate them. It essentially lets us track the exact mathematical center of where these forces explode outward or pull inward.
Let's move to and see how this builds into Coulomb's law. Coulomb's law tells us the force depends on a few key things. First, the sheer size of the charges. Second, and this is super fascinating, distance plays a massive role.
The moment these particles drift apart, that invisible force drops off sharply. And finally, we lock the whole thing in with a universal fixed number, Coulomb's constant.
When you synthesize all those elements, you get this beautiful, elegant formula. It proves mathematically that force scales up with bigger charges, but rapidly dies out the further away they move. This one formula dictates exactly how strongly 2-point charges will attract or repel one another.
All right, we now know what charge is, where it comes from, and how to calculate its force. That brings us to our grand finale, Section 4, where we map the scene of the crime where all of these invisible forces actually operate, mapping the electric field.
An electric field is essentially an invisible web of influence. It's defined as a region of space surrounding any electrically charged particle or object. If you drop a new charge into this space, it's honestly like stepping onto a fast-moving treadmill. It instantly feels a force yanking it in a specific direction. This field exists at all points in space around the object, though practically speaking, the effect can be approximated as zero if you get far enough away.
Now, what's really interesting about this is how we can visually map this invisible web. Because this web has a direction, we visualize it as dynamic arrows in space. For a positive charge, imagine force vectors bursting violently outward. But for a negative charge, those vectors act like a vacuum, pulling radially inward toward the center. It's a constant animate motion of pushing and pulling.
If you want to know just how strong that field is at a specific location, you use this simple formula. To find the field strength, you simply take the total force and divide it by our tiny test charge. Think of that test charge as just a theoretical little explorer dot we drop into the field to see how strongly it gets pushed or pulled by its surroundings. So the crucial point here is how we can bring everything we've learned today together. We can unify it all by merging our equations. By substituting Coulomb's force into our field equation, the test charges totally cancel each other out. And we're left with one ultimate formula that describes the invisible field, proving mathematically that it all just comes down to the source charge and how far away you are.
We started with two balloons pushing apart, and we've traced that mystery all the way down to subatomic particles and the invisible mathematical webs they cast across the universe. Since electric fields exist at all points in space, I want you to consider the space you're sitting in at this exact moment. What invisible vectors are bursting outward or pulling inward, pushing and pulling at the atomic level all around you right now? Thank you so much for exploring the mechanics of electric fields with me today in this explainer. Keep questioning the invisible forces in your world and keep learning.